we know that up to this point, we need to learn how to select the best features for our target learner, okay, to train it well so we can boost its performance. Now, if you guys look at these three scenarios, what do we have here? So the task is to match the figure with the corresponding statement. So looking at figure 1, we have only plotted feature 1 here, plotted feature 1 against feature 2, feature 1 against feature 3, and what we want to do is basically match the figure with the statement. So what is the relevant feature here? Can you find the relevant feature for the target classification task, the redundant feature, and the irrelevant feature? So the first one is just, you have the value of, we just plotted the values of the features, that's it. Just the values of the features. You can think of it as kind of a distribution, the first one. Okay, so guys, time. So relevant feature 1. Why is that? Because it is discriminative, right? So we can see from 0 to 1, it takes particular value. So all samples from class 1 are clustered together, and from 2 onward, you have the second class. So it's a very good discriminative feature. Now, 2. Actually, yeah, that's 2 too. Okay. I think I made it so easy for you guys. Okay, so this is basically feature 1. Feature 2 is redundant because it's correlated, right, with feature 1. So we can kind of, rule it out because we already have feature 1 that represents it captures the discriminative information we want between classes. Now the third one, what is the irrelevant feature? 3, yes. Because here, if you guys look at this way, so we can, F1 is discriminative, but if you look from this direction, okay, so what you're going to have, you will see that you cannot discriminate. There is no line that discriminates when you're looking from the third, like using F3 basically. So it's not discriminative. You can see that for a particular value of F3, you have same samples taking the same value. So like it's very irrelevant to this task. So now just by plotting, or what did we do? We just plotted the distribution of a feature across classes. Okay. And we also plotted the pairwise, that's called similarity or relationship. We explored the pairwise similarity or relationship between features, okay? So this is one way of just exploring the problem. How can we find, manually a set of good features? So this is a whole area of research. And here, we're gonna look at the first part, which is feature selection. So for dimensionality reduction, we have what we call the feature selection based methods and the feature extraction. So for the first ones, as any machine learning algorithm, we have 3 categories, right? So we have supervised feature selection methods, unsupervised, and also semi-supervised, Okay, so for the supervised, what we want when we select the features, we want that those best features or most relevant features to be correlated with the target output. So if the target output is a label, then we want, this is, to boost, for example, the classifier's performance. If it's a score, then that's a regression problem. So here, basically, the goal is to select a subset of features that are able to discriminate samples from different classes. This is for classification, or approximate regression targets. And sometimes we can do both. So there are joint classification regression models. This is something to think about, right? So now you know how each piece works, so you can think about how to put them together and solve a joint classification regression problem using, for example, linear data. So the features that are relevant are assessed by their correlation with the target label for classification problems, scores for regression problems. Now the second part, the second category is what we call unsupervised feature selection. So unsupervised, it means we don't have any labels. This can be applied for learning how to cluster data, how to group samples that are similar together, okay? By just comparing their features. So here we can learn somehow to select the best features or rank features, give them some relevant score for the particular unsupervised task. But this is a big research area, so it depends on how we define, the relevance of the feature to the, target, for the specific target unsupervised problem. Okay, now the third part is a bit easier, which means it's a mix of both, basically. You guys know that. So what do we have? We have samples with labels. We have samples with that are not labeled, so unlabeled samples. And we want to learn how to select the best features that are correlated with the target labels, but at the same time, we don't want to forget about these samples that don't have any labels. So we want to leverage them. We want to use the unlabeled samples to help us improve the selection of the best features too, that should be correlated with the target scores. Okay, so great. So now we're gonna look at two specific feature selection strategies. Okay, most of them, these two, can be are generally supervised. But let me explain. So we have two problems or two categories, and the first one is called the wrapper methods. Okay, these are learner dependent. And then we have the filter methods. These are learner independent, okay? Now, what is the key idea of the wrapper method? So let's look at this. So the key idea of the wrapper method is, first, what we have all our samples, we have all the features, okay? We put them into this, algorithm, this purple box, and we have two steps, basically. So the first step is we select a subset of features, okay? Then after that, we give this subset of features to a predictive learner, for example, a classifier, and then see how it performs, okay? So let's say, for example, I'm just gonna draw a simple example here. So I have 5 features, x1, x2, x3, x4, and x5, okay? So this is my classifier's performance. So let's say, for example, I select a subset, these 3, okay, features, and then I give them to the classifier, okay, and then I evaluate its performance. So maybe using these just 3 features, I get a, I don't know, 70% accuracy, something like that, okay? Now, in the next round, I will keep that in mind, okay, then select another subset. So, for example, these 3, okay, or maybe just 2, can be 2, just 2 features, it's a subset. So I select just 2 features, and then maybe by chance, just by selecting these 2, I get a little boost in the classification performance. So I know that these 2 generally, maybe this one is more discriminative, okay? So what is happening here is that somehow, what you guys need to keep in mind, okay, that the wrapper method first select a subset of features, see how these influence the performance of a classifier, and then update and select another subset. So the performance of the classifier is influencing the feature selection process, okay? So the performance is very important because it's guiding, it's acting as a guidance, okay? It's guiding the feature selection process in step 1. And we're going to do this over and over again until ultimately, after many iterations, after trying or testing different possible subsets or combinations of features, we get the best performance, okay? So maybe it's this feature with this one, okay? So that's how it works. So this is why we call it a wrapper method, because it wraps around. So we just, iterate these 2 steps. Now, let us sum up these strategies. So first, we search for a subset of features and then evaluate the selected features via the learner's performance and then reiterate, okay? So now this is done iteratively on all possible subsets of D features until the highest learning performance is returned. So what is the complexity of this? So how many subsets? Okay, let me keep it simple. If we have D points, okay, if we have D features, okay, these are different features, okay? How many subsets can we extract from these features? All possible subsets. So this is a combinatorial problem. Yes, 2 to the power of D. And this is very problematic because imagine if you have you have many features, right? Imagine how many combinations you need to try to get your predictive learner to find the best combination, right? Subset of features. So the wrapper methods are quite problematic because you have 2 to the power of D possible subsets of features to try, right? So this is impractical when your D is very large, okay? So what is a potential solution? Engineers, machine learners, computer scientists, they always try to circumvent problems, find better solutions. So one way is there are many papers on this. It's an active area of research, but these are 2 landmark papers where you can, for example, try to find the best first search, try to find the best subset. So trying to identify the best subset in an optimal way. Also, there's an algorithm called the genetic algorithm. So these are just, simple heuristics and approaches that you can use to alleviate the burden of, finding these optimal subsets. Now, this is the wrapper, okay? So you guys got it. It's kind of easy. So it's a learner-dependent method. We find features, evaluate, update the set, and do that over and over again. Now, the filter. Let's look at the second category. It's the filter method. Now, for the filter method, it's a simple concept. So here what we have also all features. And then what we need to do is select, somehow we use an algorithm. Let's call it a feature selection algorithm, okay? That will output a set of good features, okay? And then we will train our learner based on these features. So this is why this step is independent of the learner, because we somehow are learning how to select the best features, okay? Then we give them to the learner to train a classifier, an SVM, or a linear regression model. So these are completely independent, okay? So sometimes the filter methods can be supervised, so which means you are using the labels, and also they can be unsupervised, okay? So I will give you supervised. So I will give you a detailed example in a bit. Now, these filter methods, how do they select the best features? They rely on the intrinsic properties of the data, or they try to explore the characteristics of the data to assess the feature importance. So generally how this works, we first rank the features, so we give a rank for each feature. What does this mean? So a feature selection method, let's say, for example, this is my sample X, okay, 1. I have sample 2 and another sample, okay, so these are my samples. And my features, all my features, D features. So what this FS algorithm, feature selection algorithm, is doing, it's generating by looking at all these samples together. Oops, let me just. Okay, so by looking at all these samples together, it is it's trying to rank the features. So it's going to rank them from 1 to what? To D, according to their importance. Rank 1, this is a ranking vector, okay? Rank 1, it means this is a very important feature. Okay, rank D, it means it's the least important, okay? So for example, you might have feature 1 having rank just saying 21. This is very important feature. Maybe 200 if you have D equals to, I don't know, 500. Okay, so maybe 500 here, etc. Okay, so this is, you know, ranking the features according to their importance. So the output of this feature selection method, the filters generally, what they generate is a ranking vector. Let me write it down. A ranking vector of all features. So now, depending on this ranking vector, using this ranking vector, maybe we can select the top, just, you know, top K features. So if I select the top K, then I can just use those features. I try to find them. So this is feature number 1, 20, okay, just saying 200, 500, okay, 2, right? And I extract only those features, and I build my X1 sample reduced, okay? So this is new. I can call it R, reduced, okay? And it has how many samples? Features? K features, for example, okay? So this is how I performed feature selection based on ranking. So K here is a parameter, okay? So it depends. So how many features you will choose, that is a big problem to solve. Now let's get back to this algorithm. So the filter, the first step is to rank features. Then after ranking them, filter out lowly ranked features. So here we excluded all of those and selected the top K, okay? So, and after that, we just basically give those, the new features, those that weren't filtered out, we give them to the classifier or the learner, okay? So it's quite simple, okay? Now, for ranking the features, there are many things we can use. So ranking features can be based on feature correlation, like we just looked at this, for example, okay, this example. It can be based on defining a new similarity measures between features or metrics. Also, we can rank a feature based on its ability to reconstruct the original data from with least information loss. For example, you can think, if we go back to this case, you can think of these 5 features as the most important features that, you know, all of other features can be represented as a linear combination of these 5 features. Okay, so I have D like I5, okay? So any other feature can be represented as a linear combination of these 5. So this means, this is feature xj. So this means that these 5 dimensions, they span the whole space of the features. So you can reconstruct any original feature as a linear combination of these 5, okay, important dimensions. That's what it means. So you can, for example, you know, use that criterion to rank features. So there are many ways of doing that, okay? So I hope you guys get it, but it's clear. So to check that, I have a little quiz for you. Let's look at these 2 questions. So which method is more computationally expensive? Or we can say, okay, here is more computationally efficient, right? The second question is, which method is generally expected to be optimal for the target learning task? Wrapper or filter? So the first one, filter, very good, because the wrapper, we have a 2 to the power of d possible subset, so it's like memory, like it's very time consuming. Also can be very like memory consuming. Now, what about the second one? This is in general, of course, but you can say, oh, there are wrapper methods that are more optimal than filter methods with some heuristics, but I'm talking in general, okay? Now, for the second one, wrapper, yes. Why is that? Because the wrapper selects the features based on the performance of the learner. Okay, great.